Welcome back to Physics with Miyoshi. Today we're going to talk about more of Newton's laws. We're going to go back to Newton's second law and talk a little bit about the law of universal gravitation. Basically, I want to talk about that there are, well, before we do that, I want to talk about a couple different types of forces. There are really two different types of forces, fundamental and non-fundamental. The fundamental forces are gravitational forces, strong nuclear force, and electroweak force. And what non-fundamental forces are anything that can be, forces that can be explained by the fundamental forces. And the forces we'll be really studying, besides the gravitational force, will be forces that can be explained by the electroweak forces. Those are going to be the ones we study. Today, though, we're going to look at gravitational forces. And gravitational forces, it was discovered by, well, it was postulated by Sir Isaac Newton that there's this universal gravitational force, and that what that means is that if I have two masses, if I have two bodies, we can consider any two bodies to be points or to be spheres in space, if you will. And he postulated that there would be a force, and by his third law, there would be equal and opposite force. So there would be a force, a force exerted on body 1 by body 2, and an equal and opposite force on body 2 by body 1 that was proportional to their masses and inversely proportional to the distance between their centers. And what that translated to was an equation that looks something like this. Force is G, which is the gravitational constant, times the mass of body 1 times the mass of body 2, divided by the distance between their centers squared, or r squared. There's a guy, about 100 years later after Newton made this law, there's a guy named Henry Cavendish who measured that gravitational force, or the gravitational constant, and he came up with something like 6.67 times 10 to the negative 11th. And the units are newtons times meters squared per kilogram squared. Okay, well, what is all that really, how does that really affect us? Well, let's go back to kinematics a little bit, and we talked about G, the acceleration due to gravity. If we look at kinematics, G, and we think about Newton's second law, and we think about this thing called weight. Well, weight is really a vector pointing straight down. It's the Earth acting upon us by this universal gravitational law, and we can really figure out what that G means by thinking about weight, because weight is our force of gravity times our mass. And if we look at this equation and we can kind of look at those two, we can see that on Earth, the gravitational acceleration should be the gravitational constant times the mass of the Earth divided by the radius of the Earth square. So when we're standing on the Earth, we should experience acceleration equal to 9.8 meters per second, and you can come up with that number by doing this equation. So if I know the universal gravitational constant is 6.673 times 10 to the negative 11th, Newton times meter squared divided by kilogram squared, and I know the mass of the Earth is 5.98 times 10 to the 24th kilograms, and I also know that the radius of the Earth, about the mean radius, if you will, is 6.38 times 10 to the 6th meters. Then I can plug that into this equation, and I do get 9.8 meters per second squared. Now don't take my word for it. Go ahead and multiply these numbers out and divide by the radius squared, and you should get that number. I took the liberty of taking newtons, and Newton is a kilogram meter per second squared, and then I use and put that in here with the gravitational constant multiplied by the kilogram. So I have kilograms squared on the bottom there, and that's going to divide out with those kilograms. I have meters squared on the bottom, that's going to divide out that guy there, and we are left with meter per second squared as our units. So Sir Isaac Newton gave us lots of different things, including the universal law of gravitation, or the law of universal gravitation. Again, that says that any two bodies in the universe exert forces on each other, regardless of how far they are apart. It's just relative to the universal gravitational constant and their masses and the distance between them. So next time you go out and think about all the stars in the sky, you think about different bodies around you, just remember that they do exert a gravitation upon each other, and every particle everywhere in the universe does exert some force on you and me and every other particle in the universe. So, thanks for tuning in. We'll see you next time on Physics with Miyoshi.